Hi, everyone. Today we are presenting our paper, Timber-Dowel Reciprocal Lattice System, Design Computation to Assembly, Case Study on Tetrahedral-Octahedral Voxelization. I'm Sina Mostafavi, Associate Professor at Texas Tech University and the Director of DARS Lab, together with my co-authors, Tahmures Ghiyasi, Edgar Montejano, and Howell. We are glad to be part of this session at IASS conference in ETH Zurich.
To provide a foundation for our discussion on lattice structures, I'll briefly introduce 4 key projects that have significantly contributed to this field. First, the study on SLM lattice structures delves into their properties, performance, and the challenges associated with their application, providing key insights into their practical uses. The next is the project on cooperative robotic fabrication of timber-dowel assemblies, highlights the role of robotics in improving precision and efficiency in timber construction, particularly within sustainable building practices. Another important contribution comes from the research on the computational design, engineering, and manufacturing of a material-efficient 3D printed lattice structure. This work underscores the importance of computational tools in optimizing both design and material use in lattice structures. And finally, the development of an interactive computational design tool for large reciprocal frame structures allows designers to explore and optimize complex structural forms, driving innovation in architectural design.
Additionally, the work presented here is building on top of our one of our former projects exhibited in Venice Architecture Biennale 2023, where we were looking into lattice structures and optimizing the profile of lattice structures according to the structural optimization and structural analysis. While in this case, we were using a joint-based system using 3D printed joints. And in the presented project here, we are looking into ways to remove the joints to make the process of design and fabrication of lattice structures more efficient and jointless. The paper presentation is structured into 4 parts. We first introduced the integrated design computational workflow. Then we introduced the fabrication and assembly, which is facilitated with robotic fabrication and augmented reality. Then we introduced the material and structure, and eventually in the conclusion, we provide further details about future work and applications and further capacities of the developed workflow.
In this research, we use the voxel-based design approach, similar to how pixels work in 2D, but in 3D space, using the tetrahedral-octahedral honeycomb geometry. This method allows to transform freeform shapes into voxelated structures, which can then be used in modular design processes, such as in the Timber-Dowel Reciprocal Lattice structures. The voxels can be arranged manually or through other methods like topology optimization.
Voxelization, the 3D equivalent of a pixel, breaks down any input geometries into modular units using a tetrahedral-octahedral honeycomb pattern. These voxels form the base structure, which can be populated directly or optimized computationally. The resulting voxelated geometry then serves as the foundation for creating a stable, interlocking reciprocal system without the need for secondary materials. Reciprocalization process will start by identifying voxel sets and extracting dowels, which are represented as lines, while the remaining edges form the timber elements. The dowels are grouped based on their orientation and displaced in opposing directions to create a reciprocal system. This displacement is key as it determines the extent of reciprocalization, ensuring that dowels can interlock with the timber elements without collision. Next, dowels are extended to penetrate the timber elements, avoiding intersections. The system uses structural analysis to assign appropriate dowel thickness, and robotic milling creates precise holes in the timbers. So the result is a stable structure where dowels under compression and timbers in tension work together to maintain the overall integrity.
Our method of fabrication uses a 3D milling attachment to achieve the design, but manual methods are viable if one can drill angled holes at derived points. The tool paths are derived analytically from previous stages of the computational model, with the attachment's angles used to optimize fabrication based on our setup.
The fabrication and assembly process begins by cutting the dowels to specific lengths to align with the structurally analyzed model. The timber elements are then robotically milled to create holes at different angles and diameters to fit the dowels. Then the assembly starts with the longest dowel, which helps stabilize the structure as each timber layer is connected. Then it's being followed by the short dowels. The timber and dowels are categorized by size and length to guide the process. An augmented reality workflow is used to tag and organize timbers and dowels, helping the assembly team navigate through each step, ensuring a modular and efficient construction process.
So the integration of reciprocal geometry allows us to eliminate traditional joints, creating a seamless and jointless system. This is achieved through a consistent angular movement of all linear elements moving in different orthogonal vectors, which creates a self-balancing structure. The shift to a jointless design marks an important innovation in lattice structures, simplifying both the fabrication and assembly processes. By aligning the movement of dowels with the X and Y vectors, the system maintains the structural integrity without relying on conventional joints, which typically add complexity and potential points of failure. This is the top view of the same sequence showing the development of joint-based lattice system to jointless reciprocal lattice presented in this paper. This system employs advanced computational algorithms to optimize material usage and structural form, adhering to a resource-driven design. With only 4 sizes of dowels available, the system dynamically allocated these profiles based on the specific load-bearing requirements of each element. So through iterative simulations, we balance the structural stability with material efficiency, tailoring each component to its role. This approach ensures that the whole structure performs effectively while marking the most efficient use of the available resources, adapting in real time to meet the project's specific needs.
Culmination of our research is several one-to-one prototypes, such as the one shown. The final design, an archway which was displayed earlier in this presentation, will consist of 9 layers and stand at 10.5 feet tall when completed. Looking to the future of our research, we're developing non-standard methods of fabrication and voxelization to approximate doubly curved geometry, as with the prototypal bridge and wall samples shown. We're also experimenting with the properties of the underlying lattice, including skewed and hyperbolic geometry.
To conclude, the project shows capacities of modular assembly, especially considering the fact that after having 3 to 4 elements, each layer is stable, and this will ease the process of assembly. And at the same time, comparing to other types of lattice structure, which are joint-based, the system shows capacities for tensile strengths, which the authors are expecting to build on top of this capacity for upcoming projects. And here we would also like to thank all the people involved in this project. And also we would also extend our acknowledgement to the TTU Office of Research Commercialization for supporting the filing of this project as a US patent, which is filed in 21st of June 2024. And for more information, you can visit our website, hidars.org, and learn about more upcoming projects related to the TDRL system. Thank you.